Okay, so we were solving the following example, and we said that whenever we do the design in such case, we need to consider two extreme conditions in order to do the design. Okay, so for example, here they are asking us to find the range of weights that can be used for counterweight C if D is fixed as 2.5. Okay, so now we are fixing this distance, and then just we will have one parameter to play with, and this parameter is the value of the counterweight to select. Okay, to determine what are the two extremities, what is the minimum counterweight and maximum counterweight, we need to take the two extreme conditions. So we say, having fixed this parameter, let us consider first if I put maximum load at my end here. If I put 18 tons, okay? If I put 18 tons here, I have a risk to turn over in the clockwise direction. So I tend to rotate about B and lose contact with A. If I lose contact with A, so our A will be equal to 0. Okay, and then if I solve for sum of moments about B equal to 0, I can find what should be the minimum value of counterweight in order to not have tipping over, because the counterweight will do the balance. So there is a minimum of value that I cannot go below anyway to cause this balance. Okay, and to find the value of this minimum counterweight, all I have to do is to say sum of moments about B equal to 0. RA is 0 already because I am on the extreme case, and I risk to tip over B. And now, if I do sum of moments about B, what do I have? If I consider, for example, the clockwise direction as positive, I have first the moment of the weight. So I do 10t times this distance. Okay, this distance is the difference between 3 and 2, which is 1, plus the moment of the counterweight, which is 18 times this distance. This distance is 15 minus 2, which is 13. Okay, and this is equal to the counterweight. It should balance the moment of the counterweight. So the moment of counterweight is negative, minus WC times this distance to B. This distance to B is 2.5 plus 2, which is 4.5. And this will give me what is the minimum value of the counterweight. Because if I put a value below it, then my system will turn over B. So this is the minimum counterweight to put for this distance D of 2.5. Now I take the other extreme condition. If I have 0 load, now, I have risk of tipping over in the counterclockwise direction. So I risk to lose contact with B. So then I put RB equal to 0, and I say the equation that will give me the maximum counterweight that I can put to not tip over is sum of moments about A equals 0. And if I solve, I get that the counterweight, the maximum possible counterweight is 100 tons. So I can say then from this solution that if I fix the distance D to 2.5 feet, the range of counterweight I can use is between 54.2 and 100. Now, whenever we solve equilibrium problems, sometimes the detection of what we call 2 and 3/4 members can help us into the solution. What do we mean by 2 and 3/4 members? We'll see together. So 2/4 member is a member subjected to no couple moments, and forces are applied at only 2 points on the member. For example, if you consider the following structure, and you know that you only have two forces acting on it, one at A and one at B, and no couple is acting on the body, then you can be sure that to have equilibrium, the two forces should be opposite and should be a long line AB. Why they should be a long line AB? Because look, let us take another scenario. If they are not along AB, what will happen? So I have two opposite forces. Of course, they should be opposite to cancel out. Sum of forces should be equal to 0. But if they are not along AB, they will create a couple moment. And if they create a couple moment, then there is no equilibrium because sum of moments will not be 0. So the only possibility to have equilibrium is that the two forces should not only be opposite, but should be along line AB. Because when they are along the same line, they cannot produce any moment. Okay? So this is the condition. Whenever we say that we have a two-force member, so a two-force member is only subjected to two forces. The condition to have it in equilibrium is that the two forces should be along the line joining the points of application A and B. Let us see a figure to understand better what we are talking about. So for example, in this figure, you have one force acting at this point and the other one acting at this point. We can be sure that both forces are directed along this line. If you consider this object, we have a force acting at A, another acting at B. So the two forces should be along this line. Okay. Now, what do we mean by three-force member? When we talk about a three-force member, this means that we have a body only subjected to three forces without any couple moment. Okay, so here to have equilibrium, we have two possibilities. Or the three forces are parallel to each other, or they should pass, the three forces should pass by the same point. Why? Because let us imagine it's not the case. If you have a force F1 and F2 passing by D, let us consider that the third force is not passing by D, like this, for example. Why it's impossible to have equilibrium? Because if I do now sum of moments about D, F1 is passing by D, no moment. F2 is passing by D, no moment. While F3, because F3 it's not passing by D, then I can, if I do sum of moment about D, I consider the perpendicular from D to the force, and the moment of F3 about D will be F3 times D. So there is a moment about D. So sum of moment about D will not be 0. And we know that to have equilibrium in 3D, you have two conditions, in 2D and 3D, on a rigid body. To have equilibrium on a rigid body, we have two conditions. Sum of moment and sum of forces should be 0 about any point. If I take any point in space, sum of moment should be 0. So if F3 is not passing by D, sum of moment about D will not be 0, and then it's not possible to have equilibrium. Okay. Now, to understand better how I can use the concept of two-force member and three-force member, let us do the following example. The lever ABC is pin supported at A and connected to a short link BD as shown in the figure. If the weight of the members is negligible, determine the force of the pin on the lever at A. What do we have in this problem? In this problem, we have two parts connected together through B. We have member ABC connected to member BD. And we need to determine the external reactions at A and D. Okay? Let us say first, I want to consider the whole structure. If I want to consider the whole structure, I need to determine what are the external reactions. I have a pin at A. We said that whenever we have a pin, we have two reactions, AX and AY. And at point D, we have dx and dy. So I have four unknowns. So whenever I have four unknowns, I cannot just write three equations. I need four equations. So if I take the whole structure, I cannot solve for my four unknowns. I will write three equations and I have four unknowns. So what should I do then? I have two possibilities. Or I separate the two parts. And I take BD alone, okay? If I take BD alone, what are the forces acting on it? I have dx, dy, so I have dx, dy, and at point B, okay, I have bx, by. And now, you know that B is common between the two. We call it internal pin. So when we take BD alone, the internal pin will become external. So that's why when I take BD alone, I should consider BX, BY. And then if I take now ABC by principle of action reaction, okay, I take the opposite forces because the force of ABC on BD is opposite to the force of BD on ABC. So now if I consider it on BD, BX to the left, here it should be to the right. And if I consider BY here downward, here it should be upward. Okay, and I have, of course, AX, AY here. And I have also the 400 Newton force acting at C. Now, how many unknowns I have in this case? In this case, I have 6 unknowns. So I will have AX, AY, DX, DY, BX, BY. It's true that I have more unknowns now, but also I have more equations. Because, you know, for a certain rigid body, I can write 3 equations in 2D. So for member BD, I can write 3 equations. And for member ABC, I can write also 3 equations. So I end up with 6 unknown, 6 equations, and I solve for my system. But this is really complex. I need to write 6 equations of equilibrium and solve a system of 6 equations with 6 unknowns. If I pay attention for, in this case, that I have a 2-force member and a 3-force member, This will simplify my analysis a lot. Okay? What is the two-force member here in this figure? Which member is a two-force member? Look at member, if you look at member BD, okay? For member BD, I have forces only at D and B. So this is a two-force member. And whenever I have a two-force member, the forces should be directed along the line joining B and D. Okay, so now I can say that at D, I am sure that the force RD is along this direction. So now RD is only unknown in magnitude, but not in direction. So here I have 0, 2, 0, 2. This angle then is 45 degrees. And because I paid attention for this, if I consider now the whole structure, which is combination of ABC plus BD, I have only three unknowns to deal with: RD, AX, and AY. So then no need to write additional equations. I put three equations, three unknowns, and I am done. So this is the importance of detecting the presence of two force members. Because when I know that this is a two force member, I reduce the number of unknown. Okay? Now, if you look better also in your figure, if you pay attention well to your figure, if you consider member A, B, C, okay? So first at B, you know the direction now. It's doing 45 degrees with the horizontal. So this is RB, okay? But this system is a three-force member. Why? Because we have only application of forces at 3 points, A, B, and C. So we have a property saying that the three forces should pass by the same point. We know that the force at C is horizontal. We know that the force at B is doing an angle of 45 degrees with the horizontal. So we can be sure now that the reaction at A should pass by this point. So now the reaction at A is not in direction is known, because it should pass by A and it should pass by this point. Then instead of having to solve for AX, AY, which are two unknowns, we solve only for one, which is RA magnitude, since the angle is known. And then if you reduce your system to this extent, you only have two unknowns to solve for, RA and RB. So I was able to reduce my system from 4 unknowns to 2 unknowns if I use the concept of 2-force and 3-force member. Okay, so this is the importance of detecting the presence of 2-force member and 3-force member in my problem. Any question on this?
I have a question.
Yes.
So we know initially that the force of 400 Newton doesn't impact BD.
It will yes, it will not impact the direction of the force on BD, but it will impact the magnitude.
Okay.
Okay.
Thank you.
Welcome. So this is what we were talking about. If you take BD as system, you are sure that the forces are acting in the direction joining points B and D. So now, and here you have to assume a direction for F. You can take it down, you can take it up. And from the solution, you will know if it's really up or down. Okay? If you want, you can know exactly by doing the analysis here. If you look at your problem here, Okay, you have, as we said, it says 3 force member. So you have a force here. The force RA should pass by this point, and then we'll be able to calculate this angle as we'll see together. And you have a force passing by B. If you want to know the actual direction of F here, you say the following. This member is in equilibrium. So sum of moments about A should be 0. FA is passing by A, so it cannot produce a moment about A. The 400 Newton force is producing a clockwise moment. So F should be directed in a way to produce about a counterclockwise moment. From here, you can know that when I take member ABC, F should be downward. And this F represents what? This F represents the action of BD on ABC. So by action reaction, if the force of BD on ABC is down, then the force of ABC on BD is upward. So this is how you can make sure that you selected the right direction. And if you didn't use this analysis, it's not a problem. If you select F to be in the opposite direction, when you solve, you will get a negative result. Okay? So now, if I want to solve only for two unknowns, I need to determine this angle. To determine this angle, I need to use geometry. I say that this line should pass by the intersecting point O. And the intersecting point O, I can find it using the following. O is at the intersection of this line, which is doing 45 degrees with the horizontal. So we know that this line is passing by O. This is 45 degrees, and this is 90 degrees. So this is an isosceles triangle. And that's why the distance from this point to B, which is 0.5, is equal to this one. So now we determined that the distance to O here is 0.5 meters. And according to our figure, okay, A is situated at 0.1 meter from this level, from this line. So from A to O, this distance here in the horizontal direction is 0.4 meters. And concerning this distance here, if I consider now this distance is the summation according to my figure. If I look at my figure, I have here 0. From this level to this level, I have 0.2 meters. And then from this point to the upper level, I have 0.5. So this total distance here is 0.7. So now I can find my theta, because in this triangle, I have this is 0.7, this is 0.4. So theta is 10 minus 1. Of 0.7 over 0.4. And once you find theta, you just have two unknowns, FA and FB. To find them, you can select any two equations that you want. You can do, for example, the easiest two equation will be sum of x equals 0 and sum of y equals 0. So you write two equations with two unknowns. Okay? Any question on this? So instead of solving 6 equations, 6 unknowns, you reduced your system to 2 equations, 2 unknowns, by paying attention to 2 force and 3 force numbers. So until now, we have considered equilibrium in 2D. Now in 3D, it's the same concept, but more complex because I have more equations to satisfy. We said in 2D, we have three equations, two forces, one moment, or or one force, two moment, or three moment equations. In 3D, we'll have six equations because in 3D, the vectorial relation, sum of forces equals to 0, will give us three relations. Sum of x equals 0, sum of y equals 0, and sum of z equals 0. The same for sum of moment. Sum of moment, since it's a 3D, the moment can have, any force can have moment in three directions, in x, y, and z. So the condition for equilibrium is sum of moment about x equals 0, sum of moment about y, and sum of moment about z equals 0. So I end up with six equations, and I can solve up to six unknowns. Now, as we did in 2D, to study equilibrium, the first step is to know what are the types of supports that we have. What are the reactions that we have? For example, here, if we have several reactions that are common with 2D, and it's a cable, you know that a cable is always in tension. So the force in the cable is along the cable from the object towards the cable. So this is the action of the cable on the body. Because by action reaction, the body will do on the cable in opposite force, and the opposite force should be in a way to cause tension. That's why we say always the force of a cable on a body is from the body towards the cable. Second type of reaction is smooth surface support. Whenever we say smooth surface, no friction with the surface, so we only have the normal reaction between the two. Normal reaction is perpendicular to contact. Now, third type of reaction is the roller. A roller, like 2D, can only apply a force perpendicular to the contact line, so it will only develop one reaction on the body. Now, new types of supports that we'll have in 3D. The first one is ball and socket joint. What do we mean by ball and socket joint? So if imagine that you have here just the possibility of rotation, and you can rotate in all directions, but you cannot translate. Okay. So whenever I say ball and socket joint, it allows rotation in all directions, but prevent translation in all directions. اوكي، مثل تتفهموها اكثر. تخيلوا فيتاس السياره، اوكي، اذا محطوط على محل معين الفيتاس بقدر ابرمه، اكيد بالسيارات القديمين يعني. I can rotate it in three directions, but I cannot يعني and in this way I am not translating it, I'm just rotating it in its fixed place. So I have then, I can say that in this scenario I am like having a ball and socket joint. Okay, but in case I translate it, if I have a system where I can do translation, this will not be a ball and socket joint. So here this is fixed, this point is fixed to the ground, but and at this point I have the freedom of changing direction, but I cannot translate because this point is attached, yani this connection is attached to the ground. I cannot translate in any direction. I can just apply a rotation in all directions. So this is called ball and socket joint. And then it will develop three reactions, three forces, one in X, one in Y, one in Z. Now, another type of connection is single journal bearing. What do we mean by a single journal bearing? As you can see in the figure here, you have a circular hole at this level. Since you have a circular hole here, you can translate your rod in this direction. Because you can translate it in this direction, then no reaction is developed along this line. And you can also rotate it about this axis because you have a circular hole. So you can rotate about this axis. Whenever you can do something, if I can do a certain type of motion, then I can say that I don't have reaction developed. While if I cannot do something, then there is a reaction developed. Can I move my rod upward? Of course not. I cannot move my rod up. Okay. I cannot move it up because I have a restriction here. If you look at your figure, I cannot, I have a constraint here. My rod is inside the hole. I cannot move it upward and I cannot displace it forward or backward. So I have a reaction force in the vertical direction and I have a reaction force in this direction. The only direction where I can move is along the rod. This is why I don't have a reaction Fy. I only have Fx and Fz. Now, can I rotate about the axis of the rod? Yes. Because I can rotate about the axis of the rod, there is no moment along this axis, no My reaction. But I cannot rotate my rod like this. I cannot flip it in this direction. I cannot rotate it like this. And I cannot rotate it like this. I can only rotate around its axis. Okay? That's why we say we have a reaction moment mz, and the reaction moment is represented by a vector with an arrow like this. Okay? I cannot rotate like this, so I have a moment along z. And I cannot rotate like this, so I have a moment in x. I can only rotate about y-axis, so I don't have my. This is what we call single journal bearing. So you should be familiar with the names of connections. If I tell you single journal bearing, you directly know that I have two freedom to do here. I can translate along this direction, so no force, and I can rotate along this direction, so no moment. In the two other directions, I have a reaction force and reaction moment. Now, if they tell me you have a single journal bearing with a square shaft, since the shaft is in form of a square, I cannot rotate anymore. Okay? To rotate, I need a circular hole. I can rotate. But with a square hole, I cannot rotate. Okay? Because I cannot rotate, I have moment reaction also along y direction. So whenever they say single journal bearing with a square shaft, I have three moment reactions because I cannot rotate in any direction. The only freedom of motion here is translation in y. Since I have the possibility of translating in y, no reaction Fy. I only have reaction Fx and reaction Fz. So a single
دكتور
journal bearing with square shaft can develop 5 reactions.
دكتور ليش ما فينا نعمل روتيشن
لأنه أنت
مثل اللي قبل؟
تخيل، أنت إذا بدك تبرم شيء ما بده يكون، أنت تخيل عندك شافت هيك، فيك تبرم الرod بقلب السكوير؟ إذا الرod is of has the shape of a square, can you rotate it inside your hole؟
اوكي
بينما إذا كانت circular بتبرم. أوكي؟
بس هي انه اذا ساعة بقلب المفروض تكون بتقدر تبرم، يعني اذا هي بقلب
لا لا أكيد لا.
ما ضروري.
أنت حط شيء بساعة على القد، حط شيء بساعة على القد بهول in form of square، بيقدر يبرم؟ بفكر فيها منطقيا، ما بيبرم، ما في يبرم. اوكي، ما في يبرم because of the geometry. you cannot rotate it inside لانه في corner، في هالادج بيمنعه يعمل rotation، بينما circular shape nothing will prevent rotation of it. اوكي.
تمام.
Now, what do we mean by single thrust bearing. thrust bearing بيكون عنده مثل locking effect. يعني أنا في circular hole I can rotate بس بيكون في مثل إذا بدكم a pin هيك مثل small obstacle that is for example inserted in the hole that will not allow بيعمل locking effect. It will not allow possible translation. In this case I cannot translate. I can only do rotation. Okay. To understand this better كيف فينا نعملها فينا to put like if you want you can put a small obstacle here like this if it's closed from this side for example, or if we have like a مثل سن إذا بدكم a pin that is doing a obstruction to translation. Okay, and in this case I can only do rotation. تخيلوا إنه هون مثلا I am putting an object. Okay, I have an end here. I have an end here. So I cannot move in this direction, but I can rotate. Okay, so in this case, whenever they say single thrust bearing, this means that I prevent the translation. So I should add a reaction force along this direction. But I have the possibility of rotation. So I have five reactions, 3 forces, but only 2 moments because I can rotate about this axis. Okay. Now, what about pin? A pin or hinge? Pin or hinge in 3D is like 2D. A pin or hinge can only allow rotation about one axis. And if you look at this figure, I can only do rotation about this axis. If I call this axis X, then there is no moment reaction about X because I can rotate about X, but I cannot translate in any direction. So I have Fx, Fy, Fz. Okay, and also I cannot. This is the I can only do this rotation. Everything else I cannot do it. So I cannot translate in X, Y, Z. So I have 3 force reaction. I cannot rotate about Z axis and I cannot rotate about Y. So I have My reaction moment and Mz reaction moment. So in total, I have 5 reactions developed. I cannot do anything except rotation about the axis of the pin or hinge. The hinge is like the connections at doors that you put for doors. This connection will allow me only to rotate about this axis, and I cannot do anything else. That's why when I present the reaction forces and moment, I have 3 force reaction because I cannot